Hey folks, Ms. Gosling here. In this video, you're going to learn about field lines and equipotential surfaces. By the end of the video, you'll be able to draw field lines and identify equipotential surfaces. So let's go ahead and get started. And let's go ahead and start by talking about what field lines are. Field lines are a representation of the direction and strength of a field. So if, for example, I have an object of mass m, I'll draw my field lines that will show me, and my field lines will show me the direction in which another mass will move if it's moved into this field. So I have an object of mass m. I'll draw my field lines pointing into my object, like so. And you can see that as I get closer to the object, my field is stronger. As I move away, my field is getting weaker. So I represent the direction of my field with the direction of the arrow that I draw on my field lines to show the direction. And I actually am going to represent my strength by showing how close, by how close my vectors are to one another. So in a stronger electric field, or if my field is stronger, my vectors will be closer together. So that's my strong field. And if it's weaker, they will be farther apart. Now, I do want to mention, so with masses, we're going to show the direction that an object would move in that gravitational field. With our charges, however, as you know, if I put a positive charge in my field, it'll do something different than if I put a negative charge in my field. And we're going to show our field lines. We're going to use our field lines to show the direction a positive charge would move. So for a positive charge, if I was to take another positive charge and place it next to my first positive charge, that charge would move away. So because positive charges repel one another, I'm going to draw my field lines going out of my positive charges. And you'll notice that the distance between my field lines gets bigger the farther away I get from my positive charge. And that's because electric fields, just like gravitational fields, are less powerful when I move farther away from whatever the source of that field is. Now let's look at my negative charge. So again, I want to draw the same pattern in my field lines because just like my positive charge, my mass, the field closer to a negative charge is stronger than the field farther away from that. You can actually experience this, I think, the most easily by looking at magnetic fields. So if you've ever played with magnets, you'll notice that the closer you move the magnets towards one another, the harder it is to keep them separated from each other and the stronger the magnetic field feels. That's the same thing that's occurring with gravitational forces and with electrical forces. I have just found that for me, at least on Earth, magnets, bar magnets and the like are the easiest way to kind of experience that relationship between distance and field strength. So anywho, moving on. If I was to take a positive charge and put it in this magnetic field, or this electric field, like so, I know that my positive charge is going to be attracted to my electron. So that means that I want to draw the arrows in my field lines pointing towards my electron. So a common way to word this is my field lines go out of positive charges and into negative charges, but I think it's much more useful for you to think about how your field lines show you the direction that a positive charge will move, because that is applicable to far more situations than just this simple drawing of one or two charge systems. So let's go ahead and start by drawing the field lines between two masses. So here's my mass number 1, here's my mass number 2. Now, I know that gravitational forces are attractive. So that means that my field lines are going to be going into each of my masses. I'm going to go ahead and start with the sides that are not near each other, like so. Similarly, as I kind of get to these central points, like this, you'll see that I kind of have to start bending my lines so that they don't run into one another, because our field lines should never cross. So here is kind of a good example of what the field lines between two masses look like. Now, the next thing I want to talk about is an equipotential surface. So an equipotential surface is an area over which I can move an object without doing any work. In other words, it's an area where my potential energy is constant. So, for example, if I take my lovely blue planet, our planet Earth, the gravitational force at the North Pole is the same as the gravitational force at the South Pole, right? So if you go to the North Pole and you jump, then you go to the South Pole and you jump, you're going to fall at the same rate because you're the same distance from the center of the Earth. So what that means is that your potential energy is the same at the North and the South Pole. As a result, it actually doesn't take me any work to move you from the North Pole to the South Pole. So for example, if I was to go around the Earth like so, you would have the same potential energy at every point along the Earth's surface that you traveled through. Similarly, if I was to take you through the Earth, your potential energy would decrease. And then once you got past the center of the Earth, it would increase at the exact same rate. And again, that change in energy would cancel out. So you'd end up with the exact same energy that you started out with. So the key thing to know about equipotential surfaces is they're areas around which you do no work. Now, what does this have to do with field lines? Well, field lines show you how strong the field is. So remember that the distance between my field lines tells me how strong my field is. So it tells me how strong a force an object would feel at that point in my field. So if I stuck a mass here, the force that it would feel is different from the force it would feel if I stuck a mass closer. And in fact, it is weaker. So if I want to take a mass that's far away from the center of my object and move it closer, I need to do some work. But if I don't, then if I don't move it any closer to my center point, then I'm not actually doing any work. So if I look at my two masses, if I draw a curve that is approximately 90 degrees, so normal to my field lines, that curve is one equipotential surface. So if I take a mass that's at one point on the curve, I can move it to any other point along this equipotential surface, and it will feel it will require no work to be done. I could draw another equipotential surface like so, and I could continue drawing equipotential surfaces at increasing distances from my mass. So now let's go ahead and take a look at another scenario. Let's look at two like point charges. Two opposite point charges. So these point charges, because they are the same, because they're different, are going to attract one another. So my field line is going to go out of my positive point charge and into my negative point charge. I could do the same at the tops and bottoms of my point charges, and I could do the same thing kind of in the sides between them. I could also, of course, draw field lines coming out of one and into the other, and again, do the same on the sides, like so. So now, if I were to go ahead and take a moment to draw my equipotential surfaces, I could start by drawing a line like so, and continue drawing lines like this. I can do the same around my negative point charge. And one important thing to know about my equipotential surfaces around my charges is that the distance here is going to be bigger than the distance on the far side. So the distance between my equipotential surfaces between my charges is going to be different than the distance between the equipotential surfaces on the far side of my charges. Now I can do the same thing with two unlike charges. So in this case, my two unlike charges are going to repel one another. So we want to start by drawing field lines going out of each charge on the sides that are far away from the other charge. And I just do that because for me, it's easier to visualize that way. Then what's going to happen is if I were to take my field lines, what I'll see is that they'll actually kind of go up and down around my charges like so. And this is not quite a perfect picture, but it's good enough for government work. Now, if I were to draw my equipotential surfaces here, they'd actually look exactly the same as my masses, which is an interesting thing to think about, since we know that two masses and two charges have very different interactions with one another. Let me go ahead and fix this most recent field line because it's a little bit ugly. There we go. It's a little bit better. And so the key thing to look for here is we have field lines that are peanut shaped. They are increasingly peanut shaped the closer I get to the center, to the central, the closer I get to my two charges. So you can see here the divots here are bigger than the divots here. Now I could also look at the field lines between two charged plates. So say I took two big metal plates, and on one of them I put a bunch of protons, and on the other I put a bunch of electrons. Or say, one of them had a bunch of protons, and I took electrons, and I took some electrons off the top one and moved them to the bottom one. Now if I were to draw my field lines here, they would go out of the positive plate and into the negative plate. And because I kind of have an equal distribution of charge throughout my plates, I will draw my field lines as being exactly parallel to one another and perpendicular to my plates. The exception here is on the edges. My field lines will begin to curve and with something due to something that we call the edge effect. And the way to think about that is I have more charge on this chunk of plate than I do on a chunk of space that's half plate and half not. So the field gets slightly weaker at the edges of my plates, which is why I see that curving shape. Now, if I were to draw an equipotential surface here, I'm going to focus just on the space between my plates, so I'm not going to worry about my edges. So if I were to draw an equipotential surface, it would look like so, perpendicular to my field lines. Now, we can look at another example of a point charge. We'll say a positive point charge and a negatively charged plate. So again, my field lines are going to go out of my positively charged point charge and into my plate. And you can see things are a little weaker on the edges just because there's a greater distance between my point charge and my plate. Now the key thing so we need to know that our field lines should be radial to, so they should look like they're coming out kind of from in circles that are have increasing radii, with all of which have a center on my point charge. When I get close to this guy, my point charge, and then when I get close to the plate, all my field lines should be perpendicular to the plate to fit kind of what a field line near a charged plate looks like. So we're kind of combining our field lines between two charged plates and between two point charges. So if I were to draw equipotential surfaces here, you can see it's again pretty clear. Here's the areas where the distances between my lines are constant. So my equipotential surfaces are going to be kind of looking like circles coming out of my point chart. So those are some really important situations of field lines and equipotentials that you're going to want to make sure you know. You should know how to draw the field lines between two charged points with the same sign, two charged points with the opposite sign. You should be able to draw the field lines around a single mass. You don't actually need to be able to draw them around two. And you should also be able to draw the point charges or the field lines and equipotentials between two charged plates and between a point charge and a charged plate. So again, here's pictorial representations of just the types of situations you should be able to draw field lines for. So with that, I'm going to give you a chance to draw some field lines on your own. Best of luck and happy solving.